Today we're going to start talking about systems of linear differential equations. And by a system of linear differential equations, here I'm talking about n equations in n unknown functions. I mean a set of equations here where we have n functions, x1, x2 through xn, and we have one equation for each function that tells us how the derivative of that function is written as a linear combination of all n of the n functions that we have, plus possibly some other function. So here we have our functions x1, x2 to xn, and we write x1 of prime of t is some function p11 times x1 plus p12 x2 all the way up to p1n xn plus this extra term g1 of t. And we have similar equations for x2 prime, x3 prime, all the way up to xn prime. Now we call this system homogeneous if all the g's are 0. g1, g2 through gn are all equal to 0. Otherwise, it's a non-homogeneous system. We're going to write such a system as a nice vector system using the coefficient matrix A, where we'll write the vector x prime of t, here x of t is just the vector function x1 of t, x2 of t, all the way through xn of t. That vector x prime of t is just the matrix A times x of t plus the vector function g of t. So let's put this all together. G of t is the vector function that has these constant terms, g1 of t, g2 of t, through gn of t. And what is A? A is the coefficient matrix. A will be an n by n matrix whose entries are these functions of t, these p11 of t, p12 of t, all the way up through p1n of t, and then we'll have p21 through p2n, and down to the last row we'll have pn1 of t, all the way through pnn of t. And you'll see if we just multiply out a times x and add the vector g, then in the first entry, the first component in this column vector, the first component of x prime of t will be x1 prime, and the first component in ax plus g will be exactly this right side. And the same will be true for the second components. When we equate those, we'll get the second equation all the way through the nth components. So this is the type of differential equation we would like, or system of differential equations we like to solve. And before we actually do any solving of anything, let's talk about our general existence and uniqueness theorem. The existence and uniqueness theorem says if we're given a system in exactly this form, and we want to solve it, we want to solve an initial value problem, which means we want to find functions x1, x2, all the way up to xn, which satisfy this system and have the correct initial conditions. Here are our initial conditions. That, since here we're only talking about a first order system, the initial conditions just tell us the values of x1, x2 up through xn at some point t0. So this is a very awkward notation, but the book uses this because we need some other place to put an extra marker here. x1 of t0 is just x1 naught. The naught here will be in the superscript. This is just some arbitrary number. So this just specifies an initial value for x1, specify an initial value for x2, all the way up through an initial value for xn. The existence and uniqueness theorem now tells us that as long as all of our coefficient functions, all of the p's, and remember there are n squared coefficient functions, p11 through pnn, all of these things, and all the constant functions here, the ones at the end, g1 through gn, as long as all of those are continuous on some one fixed open interval I, and of course that I should contain this number t0 where our initial condition is specified, then there will be a unique solution. And what does that mean? A unique solution would mean telling me x1 of t, x2 of t, x3 of t, all the way up through xn of t. So one unique solution means a solution function for every one of the functions x1 through xn. There'll be a unique solution which meets the initial condition and satisfies the system of differential equations. Moreover, that solution should be valid on the entire interval I. We get this particularly because these are linear differential equations. We're not going to talk about it here because we won't really be looking at them, but if you have a system of nonlinear differential equations, just like in the case when we talked about first order, regular old single first order differential equations, there'll be a weaker existence and uniqueness theorem, and it will be very similar to what we had before. But we're going to be looking at linear systems, and for linear systems, as long as all the coefficient functions and the constant functions, that's the g's, are all continuous, meaning nice on some interval I, then we're guaranteed to have solutions to any initial value problem with initial value specified at a point in I, and this solution will be valid on all of I. How do we go about solving such a system? Well, remember, we can write this system in this form: x prime of t is a x of t plus g of t. And just as we did if these weren't vector functions but just individual functions, we're going to look at solving the homogeneous system first. If we can solve the homogeneous system, and we can find even one particular solution to the non-homogeneous, and this is our homogeneous system, then the general solution to the non-homogeneous will just be exactly as we saw before, our solution to our one particular solution to the non-homogeneous system plus the general solution to the homogeneous system. So we're going to spend our efforts in the near future talking about how to solve homogeneous systems, homogeneous linear systems of differential equations, and we'll be looking at first order systems as we have here. So how do we solve the homogeneous system? Well, again, following what we did before, we can find, if we find one solution, and by a solution I mean a vector function x of t. If we find one solution, in general, that there'll be many different ones, that won't be the full general solution. We'll want to have a whole bunch of different solutions, which in some sense are independent, and here we'll want them to be independent as vector functions. We'll talk about what that means in just a minute. But what would it even mean to have one solution? When I talk about here a solution, x1, here 1 is just in the superscript, that just means it's some vector function. This is a vector function of t. This is just some vector function of individual solutions. I'll call this x1, x2. These all have 1 in the superscript because they come from our first vector solution through xn. This is a 1 in the superscript. So when I talk about one solution, I mean a vector that contains a function for x1, a function for x2, all the way to a function for xn. That satisfies this homogeneous system. Now, my claim is, if we can find n different vector solution functions, and not just different, but they have to be linearly independent, then I claim the general solution to the homogeneous system will be the set of all linear combinations of those n independent solutions. In that case, we'll call these a fundamental set of solutions. So we'll use that same terminology as before. We'll call these a fundamental set of solutions. And here's a question: how can we tell if, when we have these n different vector functions, if they're actually linearly independent? Well, luckily, there's a version of the Wronskian that works in this case, and it's the most straightforward one you could imagine. The Wronskian of these n vector functions is exactly what you get when you take these n vector functions and put each one as the columns of a matrix. So here, the way I've written it here, my notation is slightly different from the above, so let me switch to this notation here. x1, our first vector function of t, is exactly this x11 of t, x21 of t, all the way down through xn1 of t. x2 would be that second column, all the way up to xn, which is that last column. If these are your vector functions, just put them as columns of a matrix and compute the determinant of this matrix. Now, the determinant of this matrix will be a function of t. If this determinant is never 0 on the interval I, then we have a fundamental set of solutions on your entire interval I. I want to start with just the most simple possible example of what we'll call a 2x2 system, with a system of two linear equations in two unknown functions, and ask how we solve this. First, before we even try to solve this, I could write this system as x prime of t equals the matrix 3, 0, 0, 2 times x of t. So this is our coefficient matrix A. Notice that these are constant functions of t. In general, of course, they could be functions of t. Here they're just constants, 3 and 2 and zeros. I put in the zeros there, though you could just erase those if you wanted to. And we'll see there's something very special and extraordinarily simple about this system, because the first equation really says nothing more than x1 prime is 3x1. The second equation says nothing more than x2 prime is 2x2. And we already know how to solve this system. What is the solution to this system? So a solution is just x1 of t equals e to the 3t. A solution to this equation is just x2 of t equals e to the 2t. Now, those aren't all the solutions, but I want to talk about that in terms of how we would express our solution to the system. Here are solutions to our original system. I have one solution where I can take my vector function, e to the 3t, and just the zero function for my x2. I claim that's the solution to the system. If you let x1 be e to the 3t and you let x2 be the zero function, both of these equations are satisfied. Here, if we take a second solution, x2, this different vector function, which is just the zero function for my x1 and e to the 2t for my x2, you can see immediately the zero function certainly satisfies, for x1 satisfies that first equation, and e to the 2t certainly satisfies that second equation. And here I have two different vector functions which are solutions to this system. That my claim is these are independent. That's very easy to see here. The Wronskian of x1 and x2 is just the determinant of this matrix, e to the 3t, 0, 0, e to the 2t, which is easily seen to be this times this, which is e to the 5t, which is, of course, never 0. So these are independent solutions. And what is my general solution? It would just be the vector function x of t equals c1 times x1 plus c2 times x2. In this case, that just means our functions x1 of t, x of t just means the vector x1 of t, x2 of t. That should be c1 times x1 means I'll have c1 e to the 3t, and c2 times x2 would just means I'll have c2 times e to the 2t in the bottom, and it will look like this. In other words, my general solution says x1 can be any multiple of e to the 3t, and x2 can be any multiple of e to the 2t. That's not telling us a whole lot new, but that certainly is the correct solution to these two differential equations. These are really two totally separate, independent differential equations, and I was just talking about them as a system. What makes these kind of separate is that this coefficient matrix A is a diagonal matrix, so there's no intertwining of the two functions. Notice things would be a lot more complicated if these zeros here were anything other than zeros. If we change that 0 to a 1, so I'll just make it a 1 instead of a 0 and change that 0 to a 1, then there would be a much more complicated thing here. There would be this intertwining, and we wouldn't just be able to solve one of them all by itself and solve the other one all by itself. We would really need to find, honest to goodness, dependent pairs of vector functions x of t where there was this interaction between the two that had to be dealt with. So that's really going to be the topic for the rest of this final week of the quarter. We'll start that with our next video lecture. But I wanted to give you this simplest of case, the diagonal case, the no intertwining case, so you become familiar with all of the notation and the way we talk about things.